Hey everyone, today I'm bringing you some higher level practice problems from Unit 3, Work, Energy, and Power. These questions mixing ideas from the first two units as well, and their difficulty is pretty similar to the tougher parts of an FRQ you're gonna see on your test. You'll need a solid formula fluency and deeper understanding of the physics concepts to handle them. But once you get the hang of this type of problem, you won't struggle with this unit anymore. Alright, enough talking. Let's get started. A block of mass m, initially at rest, moves on the horizontal surface with a coefficient of kinetic friction mu. At the same time, it is acted upon by a force of magnitude F that makes an angle theta with the horizontal. When the speed of the block reaches v, determine the work done by the applied force and the power delivered by the applied force. So, on your formula sheet, College Board gives you the formula for work is equal to F times D times cosine theta. I don't actually like this version because these variables are actually in the wrong order. The real idea behind the work is this. The components of the force in the direction of motion acting over some displacement on that direction. In the simple terms, when you're calculating a work, you first find the part of the force or the components of the force that points along that object's motion and then multiply that by the distance the object actually travels. So whenever you're dealing with these type of questions, start by finding the force components in a direction of motion and then multiply it by the distance along that same direction. So what your formula should actually be looking like is F times cosine theta times D. This will be more straightforward because this is a component. Multiply it by the distance it actually travels. So let's try to solve it. You're trying to find the expression for work, right? We already know the F times cosine theta, right? Because we already know the magnitude of F and the angle theta. So now we're trying to solve D. The way I approach D is using the kinetic formula Vf squared is equal to V naught squared plus 2ax. The x is a displacement you're trying to find. It's basically the same thing as D. So we already know the Vf, right? When the speed of the block reaches V, V naught, it's initially at rest, right? So V naught is 0, we can just ignore it, plus 2ax. Now we're trying to solve for A. For A, I will use the Newton's second law to find it. Because F is equal to ma, right? And then for F, for a net force, we can write a lot of expressions using when analyzing those forces. So first, let's draw a free body diagram. Obviously, gravitational force, normal force, applied force, and the friction force. F. So on the original question, it says it is moving on a horizontal surface, right? So it's not moving up or down. So vertically, the object is at equilibrium. So first, let's write the net force equation for the vertical components. Net force is equal to which components are pointing upward? Fn and the vertical components of the applied force, right? So it should be F times sine theta. Fn plus F sine theta minus Fg because it's pointing downward, right? It's equal to 0, which we can get Fn is equal to Fg minus F sine theta, not fin theta. And then we're trying to solve for the friction force. And then we will be trying to solve for friction force because it is moving on a horizontal surface. After we find the net force, the magnitude of net force horizontally, we can get the acceleration because F equals ma, and we already know the m, right? So for friction force, it's pretty simple. It's just the coefficient of the friction, multiply it by the normal force. So Ff is equal to mu Fn equal to mu mg minus F sine theta. So now we figured out the Ff. Let's write a net force equation for the horizontal components. We assume the right is the positive direction. So horizontally, there are two forces components. One is Ff, and the other one is this. What's the horizontal components of F? It's just F cosine theta, right? So let's write F cosine theta minus Ff is equal to ma. So F cosine theta minus, now we plug this back over here. F cosine theta minus mu mg minus F sine theta is equal to ma. After simplifying it, we'll get A is equal to F over m times cosine theta minus, no, plus mu sine theta minus mu g. And this is the expression for A. Now, let's plug the expression for acceleration back to the kinetic formula, which is Vf squared is equal to V naught squared. V naught is 0 because it's initially at rest, right? It's equal to 2ax. Vf squared is just equal to 2ax, which is equivalent to 2 F over m. Actually, use a square bracket here. Cosine theta plus mu sine theta minus mu g times x. Vf is just equal to v, right? V squared, which we will get x is equal to v squared over 2 F over m. Cosine theta plus mu sine theta minus mu g. And now we already find the expression for the displacement. So we only need to multiply it by F times cosine theta, which will get the final answer. Work is equal to F cosine theta F times cosine theta times v squared. Don't simplify it, because you actually find some surprising things when you're doing the power. Now let's try to solve for power. The formula for power is P is equal to W over T. How do we find T? Using kinematic formula, Vf is equal to V naught plus AT, right? V naught is 0, so we can just ignore it. So T is actually equal to V over A. Then we can just plug in the acceleration we find originally over here. So we can find t is equal to v over f over m times cosine theta plus mu sine theta minus mu g. And then we can plug p back to the original. P is equal to w over t, right? And then p is equal to w over t is basically equal to w times 1 over t, right? So it will equivalent to p is equal to multiply it by f over m cosine theta plus mu sine theta minus mu g over v. This one's supposed to be v squared. Well, now you can see that, oh my, we can cancel out a lot of things. F over m times cosine theta plus mu sine theta minus mu g. This is the exact same thing we can cancel them out. And then v, here's a square, here's a v, so we can cancel it out. So we basically cancel out entire time, which will finally, we will get to our final answer. P is equal to half f times v times cosine theta. That's why I prefer calculating with letter first, because you will see that there's actually a lot of things you can cancel out. In this case, in this question, we can see that the power actually has nothing to do with the acceleration because we completely cancel out the acceleration over here. And finally, we'll give you a very simple answer. P is equal to half f times v times cosine theta. A block of mass m slides down an inclined plane of height h that makes an angle theta with a horizontal. The block has an initial speed v1 at the top of the incline and reaches the final speed v2 at the bottom. Determine the coefficient of friction between the block and the surface of the incline. So for this type of conservation of energy question, the first thing you need to do is write down the equation of the conservation of energy. So first, let's analyze what type of energy exists when the block is at the top. The block is moving at an initial speed v1, right? So it definitely has the kinetic energy, and it says h above the ground, so gravitational potential energy exists. So let's write down mgh plus 1 half mv1 squared. This is the amount of energy it has when it's at its initial position. And when the block reaches the bottom, it only has a kinetic energy, right? Because it is not above the ground at all at this moment. So this much energy supposed to be equal to 1 half m times v2 squared. The reason why I said it's supposed to be equal to is that if there's no friction exist on the incline, these two will be equal. However, now the friction exists, so the friction will do work, right? And it will actually cancel out some of the energy during the entire process. So over here, we should write minus work done by the friction force. So how do we calculate the work done by the friction? Work done by the friction obviously is equal to friction force times the distance it travels. And FF over here is equal to the normal force times mu. Do you now see that everything actually comes together? Like when you originally see the question, it gives you V1, gives you V2, And you may think there's nothing that can actually relate it to the coefficient of friction, but actually it can. It's right here. So how do we solve the expression for the normal force? Let's just draw a free body diagram. This is Fn, this is Fg, and this is Ff. And also, over here, you don't really need to put cosine theta here because the angle between the friction force and the direction that the object is moving is actually 0 degrees. And cosine 0 degrees is equal to 1, so we ignore it over here. And also, the block is not like moving straight up towards the surface or even break into the surface, right? So the object is at equilibrium in the direction vertically to, relative to the surface of the incline. So we can just write the components or write the net force equation out. This is theta. Net force y towards incline is equal to Fn minus Fg times cosine theta equals 0. So we can get Fn is equal to Fg cosine theta and it's equal to mg cosine theta. So now let's plug mg cosine theta back to the original function, which we can get the work done by the friction is actually equal to mg cosine theta times mu times d. Well, before we plug it back to the original function, we should simplify it to the version that we love to see. For example, we will put work done by the friction on one side and the other expressions on the other side. And then after we simplify, we'll get Vf is equal to mgh plus 1 half m times v1 squared minus v2 squared. And then let's plug this back here. So now it will be mg cosine theta times mu times d. D is the distance it travels along the incline. So this is h, right? Distance it travels, it would just be h over sine theta. And that's equal to mgh plus 1 half v1 squared minus v2 squared. And then you can easily see that m can be cancelled well. And then let's move everything over here except for mu to the other side. So we divided them on both sides, which will get you the final answer. Oh, I forgot there's an m here. Which will get you the final answer. Mu is equal to tangent theta times v1 squared minus v2 squared over 2gh plus 1. And that is your final answer. There's a tangent h exists because cosine theta over sine theta is equal to cotangent theta or 1 over tangent theta on the left side. So if you want the right side to get tangent theta, you multiply it by tangent theta. And then m can be cancelled out. Yep, I think that's correct. Alright, A block of mass m moves on a horizontal surface. When the block has a speed v, the end of the spring, with a spring constant k, is at a distance d from the block. Assume the block is still moving when it's contact with the spring. Part A. If there's no friction on the horizontal surface, determine how much the spring will compress. So for part A, it's pretty simple. Since there's no friction on the horizontal surface, so the work done by friction will not cancel any energy the block originally have when it's moving at a constant speed v. So simply we can just write 1 half mv squared is equal to when the block suddenly touch to the string, right? It still has a velocity of v. And after the spring is compressed, like this much of distance, the block will stop moving. And at that moment, the block only has a spring potential energy, which is half k times delta x squared. So easily we can get delta x is equal to square root of mv squared over k. You will pick the positive solution here because it asks you how much the spring is compressed. So it's actually asking you for the magnitude, not the displacement. So you actually pick the positive value here. So this is your answer for part A. Now for part B. If the horizontal surface now has a kinetic friction with the coefficient of mu, 1. The instantaneous speed of the block at a moment of contact with the spring. So now it's basically the same thing, but now friction actually does some work to cancel out the initial energy or the initial kinetic energy that the object has. So initially, the block has a kinetic energy of 1/2 m times v squared minus when it's on the ground level, right? The normal force is just equal to the gravitational force, and the gravitational force is just equal to mg minus mg times mu times d, and it's equal to 1/2 m times v1 squared. This v1 is not the same v as the previous one because that's the new speed when after the block has traveled the distance d along the horizontal surface. So after simplify it, we will get v1 is equal to square root of v squared minus 2g times mu times d. Part 2. Write an equation for calculating how much the spring is compressed. You don't need to solve it. So still, the original amount of energy the block has is just 1/2 mv squared, right? Because it's moving at a horizontal surface with a constant velocity of v minus work done by the friction. And after that, it's supposed to be equal to 1/2 k times delta x squared. As you can mention that I actually leave some space blank here because you actually forgot about something. When a spring is compressed, the block is still moving along the rough surface for this much of distance. It's actually delta x. I forgot there's a square here. So you should actually, on the left side of the equation, you should actually minus the amount of work, friction done in this part of the section. So we can write minus work done by the friction, part 2. So for work done by the friction originally, we can just use the stuff we get from the last one, 1/2 mv squared minus mg mu times d minus the friction force is still the same, right? When it's traveling in this section, it's still mg times mu. And over here, so it will be mg times mu times delta x. And it is equal to 1/2 k times delta x squared. So because the reason that you don't need to solve it, you can just stop right here. But if it actually asks you how to solve it, I'll just tell you a way to solve it. Because as you can see, you're trying to solve for delta x, right? You're trying to solve for delta x. So you can actually reorder the entire function to be a quadratic function and using the formula for calculating the roots of the quadratic function, which is x is equal to 2a negative b plus or minus square root of b squared minus 4ac. You can just solve it in this way, but this will 100% not be on your AP test, so you don't need to worry about it. You can just stop right there. A block of mass m initially at rest on a smooth incline plane that makes an angle theta with a horizontal. The end of a spring with a string constant k is located at a distance d along the incline from the block. When the block reaches a spring, determine 1. The instantaneous speed of the block at the moment of contact with the spring. So over here, you have to have the mindset of like energy transformation. Like originally when the block is over here, it only has a gravitational energy, right? And when it reaches over here, when it reaches at the moment when he contact the spring, all of the gravitational energy transformed to the kinetic energy. So we can just write initially it has the gravitational energy of mgh is equal to 1/2 mv squared. And how do we get h? The h is basically the distance from here, from this point to this point, and we already know the length of the incline is d. So we can just using trigonometry, we can get the height is actually equal to d times sine theta. And then we can plug h, the value h, back to the original function, which we can get mg times d sine theta is equal to 1/2 mv squared, which will give us the answer v is equal to square root of 2g d sine theta. Alright, part 2. Write an equation for calculating how much the spring is compressed. You don't need to solve it. From the previous part, we already get as soon as the block touches this end of the spring, it has an instantaneous velocity of 2 g d sine theta. So by the way, this is the distance from this point to this point. And now it's asking you how to calculate how much the spring is compressed. So now we should assume that the spring compressed this much of distance. And the blue spring is the length of the spring after it has been compressed. So the key thing in this question is which level is the ground level. I'll just tell you that we usually assume that when the spring is compressed this much, we assume the lowest point is the ground level. Okay, so this part is delta x, which means this part is also delta x. So at this point, block has two types of energy, right? As soon as it touched the surface or touched one end of the spring, it has a kinetic energy of 1/2 m times v squared. And v over here is this, plus mgh. Because at this moment, if this surface is ground level, it is still like this much above the ground level. So there's also mgh over here. And it is equal to 1/2 k times delta x squared. And now let's plug in some values. We already knew that v is equal to square root of 2 GD sine theta, right? We can just write, and v squared is just 2 GD sine theta. We can just write m times GD sine theta is equal to, no, plus m times g. How do we solve for delta h? For h. So we'll solve this part as h. This is delta x. This is theta. So delta h, so h is basically like using trigonometry, it's basically delta x times sine theta times delta x times sine theta. And it's equal to 1/2 k delta x squared. So you can just stop it over here, and this is your answer. However, if you want to solve it, just move everything on one side of the equation and solve it as a trigonometry. You just solve it as a quadratic formula, a quadratic equation, and using the formula for the root, which is negative b plus or minus square root of b squared minus 4ac over 2a. But it's not gonna be on your test, so don't worry about it. Alright, now let's combine the ideas of conservation of energy with circular motion we learned previously. A block of mass m moves with uniform straight line motion on a horizontal surface, and then enters a vertical circular track of radius r. Then the highest point of the circular track is labeled A. If the normal force exerted by the block on by the track on the block at the top point A is required to have a fixed value of Fn, find the minimum speed the block must have while moving on a horizontal surface. So we are trying to solve for V. First, we have to identify how many energy it has when it's moving on a straight line horizontally. Because of conservation of energy, also there's no energy lost, the amount of energy the block has will be constant throughout the entire process. So let's just find a point on the circular track that is easier for us to find the value or the amount of energy it has. So I would just pick point A because it's easier. At point A, it definitely has gravitational potential energy, right? Because it's this much above the ground. Also the object is also moving along the circular track, so there's definitely a kinetic energy on the block. So the energy it has on point A is equal to 1/2 mv squared plus mg times 2h, or 2r, 2 radius, right? Because this is 1 radius and this is 2 radius. mg times 2r. However, we don't know what's the value of v here, so let's try to solve it. How do we solve for v? And it's time to use the concept of the stuff or the formulas we learned from the previous unit or previous part, the circular motion. At the very top of at the very top of the circular track, the object has two forces: normal force and the gravitational force. We know both of the values of normal force and gravitational force, so we can just write Fn plus mg is equal to, since both of these forces are pointing towards the center of circle, so it's equal to Fc. And it's equal to m times v squared over r. And we can get v squared is equal to Fn times r over m plus gr. We don't need to square root that because over here it's just v squared, so we don't need to do an extra step. Plug this value back here, which we can get the energy at point A is equal to 1/2 m, well, no m, 1/2 times Fn times r plus mgr plus mg2r. And this amount of energy is equal to the amount of energy the object has when it's at the bottom of the circle or over here is equal to energy initial, which is equal to 1/2 mv squared, v naught squared. So now you can solve for v naught. V naught will be equal to square root of Fn times r over m plus gr plus 4gr, which will be v naught, and it is equivalent to Fn times r over m plus 5gr. And this is your final answer. Now let's make the question a little bit more complicated. A block of mass m slides down from the top of a smooth inclined plane A, which makes the angle theta with a horizontal. It then moves across a horizontal surface of length d and smoothly transitions onto a smooth vertical circular track of radius r. A. If the horizontal surface is frictionless, determine the minimum height of the incline which the block must be released to ensure that it remains in contact with the circular track all times. So for this type of question, it's still using the ideas of conservation of energy, but the most important thing for you to do is to find a point on the graph that is very easy for you to determine the amount of energy using the variables you already know. For example, in this question, I will just pick point A. So for point A, the amount of energy it has is gravitational potential energy because it's that much above the ground. I can just tell you it's 2r because there are two radius. It's equal to mg2r times 2r plus, since it's on the circular track, right, it definitely needs to be moving. So it also have 1/2 mv squared. And EA, the amount of energy it has at point A, is equal to the amount of energy of the block has at its initial position, which is equal to energy it has at initial position is equal to mg times h. And h is the variables you're trying to find. How do we find v? The situation that it remains in contact with the top of the circle is that when the normal force at the top is very, very close to zero, right? We already talked about in a previous video. And so we can just write the net force equation at the top is just equal to mg. And it's equal to mv squared over r, right? Because there's only one gravitational force pointing towards the circle. And we can get v squared is equal to gr. We don't need to square root that for now because for the kinetic energy, there's v squared exists. So we can just plug gr back to the original function. EA is equal to, oh, this one's supposed to be capitalized R. UA will be equal to mg 2r plus 1/2 mgr, and this equals to mgh. And now we can see that these mg can be actually cancelled out. After we cancel out them, we can get h is actually equal to 2.5r. Alright, part B. If the horizontal surface has a kinetic friction with coefficient mu, determine the minimum height on the incline from which the block must be released to ensure that it remains in contact with the circular track at all times. This is actually a little bit different from the previous part since the horizontal track, this part actually has friction. So the work done by the friction will actually cancel out a little bit of energy the object has when it's at the original position. And however, the amount of energy it has at point A doesn't change since the amount of speed it requires to remain contact with the surface is still not changed because the centripetal force is still equal to only Fg. And the height doesn't change as well. The height is still 2r. So we can just use the conclusion we get from the last part. And the energy at point A is equal to mg2r plus 1 half mgr, and it's equal to 2 over 5 mgr. Now, here's a trick to solve this question. We now need to analyze the amount of energy it has at the bottom of the circular track, because we can actually write two equations to express the amount of energy it has at point B. Let me explain why. The first way for you to write it is looking at this way. Since the track is smooth, right? So there will be no energy loss when the object is moving from B to A. So the amount of energy it has at point B is also equal to the amount of energy it has at point A. It is also equal to the amount of energy it has when the object is sliding down the slope and reach point B. So it will be the amount of gravitational potential energy minus the amount of work done by friction. So it can be also equal to mgh minus work done by friction. The work done by friction here will just be the friction force times d, and it's equal to Fn times mu times d. And since it's a horizontal surface, so the normal force will just equal to mg. So the work done by the friction force will just be mg mu times d. Let's plug the work done by friction back to the original function, which is over here. And this is equal to mgh minus mg mu d. And this is equal to the amount of energy it has at point A, which is 5 over 2 mgr. And you can see mg, these mg's can be cancelled out, which can give us an equation that said h minus mu d is equal to 5 over 2 mg, no, 5 over 2r. This one's supposed to be capitalized, be careful. So now, we can write the expression for h. The new h will be 5 over 2r plus mu d. Now, let's try to make the question a little bit more interesting. A block of mass m slides down from the top of an inclined plane A with height h and angle alpha to the horizontal. It then moves across the horizontal surface and smoothly transitions onto a vertical circular track of radius r, where r is smaller than half of the h. After passing through the circular track, it continues onto another inclined plane B, which makes an angle theta with the horizontal and has length d. Friction can be neglected. Part A. 1. Find the speed of the block when it reaches the ground after sliding down the first incline. Well, this part is pretty obvious since there's no friction, right? So the mechanical energy the block has at the top is equal to the mechanical energy it has at the bottom. So when the block is at the top, what kind of energy does it have? Since it's not moving when it's at an initial state, so it only has the gravitational potential energy, which we can write mgh. And it's actually equal to, when it's at the bottom, it's no longer above the ground, and it's moving at a speed. So it only has the kinetic energy, which is 1 half mv squared. After simplifying that, we can get v is equal to square root of 2gh. So now part 2. During the motion in 1, determine the work done by the gravity. Well, here's a little trick. Whenever it's asking you how to determine the work done by the gravity, you just use the gravitational force that the object has, multiply it by the vertical distance that it traveled. So in this situation, the work done by the gravity will just be Fg times h, which will be mgh. Pretty simple, right? Part 3. During the motion in 1, what is the power delivered by the gravity? So here's my thought process. Since the formula for power is equal to work over time, we already know the work. So we're trying to find time, obviously. How do you find time? So the object is initially at rest and it's moving down the ramp, right? There's definitely a force component that is pulling it downwards. And this force components actually create an acceleration. After we find that acceleration, we can use a kinematic equation to find the time. And how do we find that acceleration? I decided to use Newton's second law, which is F equals ma. Before we use it at F equals ma formula, we should analyze the force first. So let's first draw a free body diagram. When the object is at a ramp, there's an Fn and Fg. I'll just write mg. And that's all. That's all the forces that act on the block when it's moving on the ramp. So now let's separate them to components. Since during the entire process, the object is not like flying away from the ramp or break into the ramp, so as in the direction that is perpendicular to the ramp, it's actually at equilibrium. However, at the direction that is parallel to the ramp, it's actually not at equilibrium because look here. Look here. There's actually a component that pulls the object to move down the ramp. So how do we find this components? As we know, this angle is alpha. The components would just be mg sine alpha. After we find the force, let's write the net force equation down. Net force, x direction relative to the ramp, is equal to mg sine alpha, and is equal to ma, which we can get a is equal to g sine alpha. After we find the acceleration, which kinematic formula should we use? We already know the distance it travels. We already know the acceleration. So I would suggest you to use x is equal to v naught t plus 1/2 at squared. Since it's initially at rest, we can basically ignore v naught t. So x is equal to 1/2 at squared. How do we find the distance it travels? Using the trigonometry, right? Very simple. The height is h. We're trying to find how long this is, and we already knew the alpha, which we can get x is actually equal to h over sine alpha. So now after simplifying them, we can get t squared is equal to 2h sine alpha times g sine alpha. After we square root it, we will get t is actually equal to 2h over g inside the square root over sine alpha. So this is your time. Plug the time back to the power, which we can get the power is actually equal to mgh times sine alpha over square root of 2h over g. Alright, now part B. 1. What is the speed of the block when it reaches the highest point of the circular track? So this is actually pretty easy. Since there's no friction, so the mechanical energy the object has when it's at the initial position is equal to the mechanical energy it has when it's at the top of the circle. So we can just write initially what kind of energy does it have? Only have mgh, right? Only mgh. So yeah, only mgh because it's not moving at the beginning. And when it's at the top of an incline, what type of energy does it have? Of course, gravitational potential energy, mg times 2r, because it's 2 times radius above the ground, plus the speed it has when it's at the top of the circle, plus 1/2 mv squared. So we're trying to solve for v. It's just reformula we can get M can be easily cancelled out. So GH minus 2GR is equal to 1 half V squared, which V will be equal to 2GH, square root of 2GH minus 4GR. And this is the correct answer for the first part. So now let's look at the second part. To ensure that the block remains in contact with the circular track at the highest point, from what minimum initial height on the first incline must the block be released? So still, basically the same thing as the previous problem we did. When it wants to remain the minimum contact, the Fn is very, very close to zero. We can just approximate it to zero. So at the top of the circular track, the centripetal force is only equal to Fg, and that's equal to mv squared over r. And Fg is equal to mg, right? Which v we can get is just equal to square root of gr. So now at the top, it has a mechanical energy of mg times 2r plus 1 half times m times v squared is just gr, right? G times r. Oh, my bad. This place is supposed to be capitalized r. And this is equal to mg times h1. So for solving h1, we can easily see that mg can be actually canceling out. So h1 is equal to 2.5r. This is a minimum height you must drop the object from, or the object will not remain contact with the top of the circular track. Now let's look at part C. After the block leaves the circular track, 1. What is the vertical height of incline B? Well, that's pretty obvious since we already know the length of the incline and we know the angle. It is above the horizontal surface. So the height will just be d times sine theta. That's free. For the second part, what is the speed of the block at the top of incline B? Since there's no friction in the entire track, right? So there will be no absolutely zero mechanical energy loss, which means the amount of energy it has at the top of the incline is equal to the amount of energy it has at its initial position. So we can just write the conservation of energy equation down, which is mgh is actually equal to mg h2. I would just assume this part is h2 plus 1 half mv2 squared. We're trying to find v2. And we already know that h2 is equal to this, right? And obviously m can be cancelled out. After we cancel out m and plug in h2 is equal to d sine theta, we can get gh is equal to gd sine theta plus 1 half v2 squared. After simplifying it, we'll get v2 is equal to the square root of gh minus gd sine theta times the square root of 2. Well, you can actually put square root 2 to the front to make it look better, but now let's look at the most interesting part of the entire FRQ, part 3. After leaving the incline B, the block moves as a projectile. What is the maximum height it can reach relative to its original release height, h? Is it greater than it, equal to it, or less than it? Explain your reasoning. Well, some of y'all may think, oh, since there's no friction or absolutely no energy loss throughout the process, as soon as when after the block leaves the incline B, as soon as it stopped in the midair, the height it has above the ground would definitely equal to h because of the conservation of energy. Or actually, you're wrong. As soon as the block leaves the incline, it will have the velocity vector that looks like this, which both have the horizontal components and the vertical components. So it's basically like moving in a projectile motion. What you basically is thinking is, if you said it stopped during the midair, what it actually means is the vertical speed will be equal to zero. However, horizontal speed will always exist. So at the highest, at the maximum height, it actually has the mechanical energy of mgh3 plus 1 half m times vx squared. Because you already learned the projectile motion, right? The horizontal components will never disappear throughout the entire process because there's no external forces or force components that act on the object horizontally. Yeah, because during the projectile motion, it's basically doing a free fall, and it only has a gravitational force that act on the object, right? So this is equal to mgh, right? Because conservation of energy. Obviously, this is greater than zero because m is greater than zero, vx is greater than zero, so the entire thing is greater than zero. And mgh minus a positive thing is equal to mgh3, which we can easily get that h3 will actually be smaller than h. Well, that's the explanation. How do we write the actual answer? Well, I will not write it down in my videos right now. Go check my answer doc in the description down below. Now on the next one. A light inextensible rope of length L is attached to a fixed point on the wall. At the free end of the rope hangs a small cubed shaped wooden block of mass m. Neglect the block's dimensions. Initially, the rope is pulled so that if it makes an angle theta with a vertical, at which point the bottom of the rope is at a height h above the ground. The block is then released and swings along a circular arc defined by the rope. Scenario 1. Block detaches at the lowest point. If the block loses contact with a rope at the lowest point where the rope is vertical, determine the instantaneous speed of the block at the moment of release. So from the question, we know that the initial height of the block above the ground is h. The length of the rope is L. So initially, it only has a gravitational potential energy, right? And when it reached the lowest point, it also has a gravitational potential energy, but it's smaller. It also has it also has the kinetic energy because it is moving at some speed, right? So we can just write mgh is equal to 1 half mv squared plus mgh1 because it is h1 above the ground. How do we find h1? Now we actually need to use a little bit of geometry here. Let's pull a line here. Since this is L, so we can find this part. This part will be L times L times cosine theta. And the total length will be this plus this, which will be total length L times cosine theta plus h. And now we're trying to find h1, right? h1 would just be the total length minus the length of the rope, which will be h plus L times cosine theta minus 1. And now we already know the h1. Let's plug this back to the original formula. mgh is equal to 1 half mv squared plus mg times square bracket h plus L times small bracket parentheses cosine theta minus 1. And m can easily be cancelled out, right? We're trying to find v, so we put v at one side of the equation and every other thing at the other side of the equation. So we can get something like 1/2 v squared is equal to mg is equal to gh minus g times square bracket gh plus L times cosine theta minus 1. And after the simplification, we'll get the expression for v, which is equal to the square root of 2gl. Well, I actually write an extra g here. It's supposed to be only h. It will simply be 2gl times 1 minus cosine theta. Well, if you're confused on why I got this answer, you can simply see that gh can be canceled out, right? Because it's a plus gh minus gh here. And then after we cancel these out, the only thing left will be L times cosine theta minus 1. However, cosine theta minus 1 will always be negative. So after we flip it to 1 minus cosine theta, the negative sign in front of it will disappear. So it will become something like 1/2 v squared is equal to gl times 1 minus cosine theta. And then we times 2 on both sides of the equation, which will be 2. And v squared is equal to this. And then we square root that, we'll get our final answer. Well, this part is not that bad because the basic conceptual stuff are literally the same, which is conservation of energy. It's just a little bit complicated on the algebra part, but you can just be a little bit careful on that and you'll be fine. Now let's look at part 2. Determine the horizontal distance traveled by the block before hitting the ground. The distance the block traveled horizontally is actually equal to the velocity, or the horizontal components of the velocity, times the time it took for the block to reach the ground. By the way, the Vx will never change because during the time when the block is flying in the midair, it is doing a free fall. And the only force that acts on the object is gravitational force, which means there will be no contributes or components to contribute to the horizontal components, so Vx will never change. So how do we find Vx? Well, let me tell you this. At the lowest point on the trajectory, when the block detaches from the rope, its instantaneous velocity is along the tangent to the circular path at that point, which happens to be horizontal. And this is because in a circular motion, the velocity vector is always be perpendicular to the radius. So at the bottom of the swing, the radius of the circle points straight upwards towards the pivot, like this, right? So the only direction perpendicular to that is horizontal. What that means is the velocity you get from previous part are all horizontal components. Or in other words, the velocity you get from previous part, the direction of the velocity you get from previous part is actually horizontally. It's actually towards the horizontal direction. Isn't that surprising, huh? So this is your Vx. So how do you find t then? T is the time that it took for the block to fall from this high or this tall to the ground. So we can just use simple kinematic equation, which is x is equal to v naught t plus 1/2 gt squared. Because it's doing free fall, so acceleration will just be g. And since originally the velocity that the object has is only towards horizontal direction, so the initial vertical components of the velocity will be 0, so we can just ignore that. And x is just your h1. So now let's plug in the values. H plus L times cosine theta minus 1 is equal to 1/2 g t squared, which we can get t is equal to 2h plus 2l times cosine theta minus 1 over g. And now let's multiply this t to the v we find previously. I'll just write it here. Dx is just equal to everything are under the square root of 2GL times 1 minus cosine theta times 2h plus 2l times cosine theta minus 1 over g. Well, you may think that's a little bit complicated, but we can actually cancel a lot of things. For example, we can cancel out g, and we can move these 2's outside of the square root, which we can get our final answer, dx, will simply be 2 times L times H times 1 minus cosine theta minus L squared times 1 minus cosine theta squared.